So building on the NHRC theme this year of housing outcomes relating to why housing matters, the 2015 Sustainable Housing Working Session will explore how to achieve desirable social, economic, and environmental outcomes through housing, with a series of presentations that illustrate the process steps and linkages that occur between an initial housing design concept or intent and the final built form and achieved outcomes, including validation through performance monitoring and post-occupancy evaluation. Christopher will now take us through today's program.
Thank you, Thomas, and welcome, everyone. We have 3 presenters today that bring a wealth of experience to share on the topic of achieving positive housing benefits and social outcomes. The presentations will showcase housing design projects and development approaches that establish clear performance metrics linked to desired outcomes, follow an integrated design process, utilize research, modeling, and visualization tools, and consider occupant roles and behavior as part of the solution set. Note that this session is being video webcast live in both official languages to reach all stakeholders interested in Canada's sustainable housing research and practice. We are also recording today's webcast presentations as video clips for viewing after the meeting. They will be available on the NHRC website, which is a great resource for everyone interested in housing research. Before we get into the meeting proper, may I remind you of a few items to ensure the smooth functioning of our meeting. Would you please turn off your mobile phones and any mobile devices that transmit? When speaking, please state your name and use the microphone in front of you, and don't forget to turn on and off the microphone. Respecting this procedure will ensure that everyone is able to hear all of our comments, especially our webcast audience, translators, and our meeting recorder. May I also remind you to take out your session evaluation form from your meeting package and keep it handy so that you may fill it out as we go along. Your feedback is important to assess the effectiveness of this meeting and for planning future meetings. Each item on our agenda has a built-in amount of time for questions and answers after each presentation. So without further ado, I will ask Thomas to introduce our first speaker. Thomas?
Thanks, Chris. It's my great pleasure to introduce you this morning to our first speaker, Mr. Cianforne. Christian is a principal and the Building Energy Practice Lead at Morrison & Hershfield in Vancouver. Christian has nearly a decade of experience consulting on energy efficiency in the built environment. His primary focus has been on using energy simulation tools to assist in the decision-making process for new construction projects, to document compliance with building codes and LEED, and to optimize existing building operations. Christian sits on the Energy Technical Advisory Groups for both the CAGBC and the U.S. Green Building Council. He is an instructor at the University of British Columbia and is the co-founder of the Energy Modeling Institute, a nonprofit dedicated to delivering energy literacy through education and professional development courses and workshops. Christian's presentation today is on energy optimization techniques for better outcomes. Development of new tools and processes in energy simulation allow for large parametric modeling studies to be completed cost-effectively. The benefit of these studies is that they provide significantly more insight into the impact of building system variables, both in isolation and in combination. Coupled with advancements in data visualization, the results can be easily communicated to project teams in an integrated design charrette setting, providing significantly more flexibility towards achieving project energy outcomes, including reductions in capital costs. Please join me in welcoming Christian.
Thank you, Thomas. Morning, everyone. I guess I'm the energy efficiency. That's the first outcome I guess we'll focus on today. What I'm going to build up to is a new, I guess, not so much new, but a new technique to looking at how to optimize energy performance during the design setting. I think Thomas will go on to talk about monitoring and verification of built projects and how they're performing, but this will focus on how do we engage the design team to set ourselves up for better outcomes during that early process. And I will have probably half of the time I'll be spending demonstrating this process through case studies related to sustainable housing projects ranging from small single-family all the way up to high-rise multi and residential buildings. So I'll cover the energy model. I like to always reset people's understanding or expectations of what an energy model is, how do we use it on projects. There's always a lot of attention paid to, what's the validity of models that are used to make these decisions. So I'll review some of that, and then I'll go into its role and purpose, primarily, again, in the design setting, and look at some of the challenges that project teams face in any sector with regards to how do you optimize energy efficiency early in design with limited information. I'll get into new methods, and then I'll show the case studies and demonstrate some of these new methods in practice. And then we'll look at, did we actually achieve the better outcomes in the process? So I like this image. It's essentially just a schematic design showing the complexities of a building. It's not my image. I think it's a Renzo Piano building somewhere in the world. But it highlights all the different building systems and their interrelated connectedness, and it shows how complex energy use in a building can be. And when we look at energy models or trying to mimic this energy use, we have to understand that the models have to be as complex as the building in order to get the numbers right. And so in fact, what we see here is there's a lot of things happening in this building which our models have to capture in order to be able to inform design in the right way. And so we have to look at, what is the weather of the project site in question? And not only what is the weather on a sort of high level, but often these simulation tools are doing calculations for every hour or even more frequently over an entire year. And these complex calculations not only take into account weather, they have to look at the performance of the building envelope, how much heat is coming out of the envelope, how much heat is coming in through windows, what are the behaviors and patterns of occupants, of lighting, of equipment, mechanical systems, anywhere from where heat is being generated through how it gets pumped and blown throughout the building with various equipment, its efficiencies, controls. There's thousands and thousands of inputs that go into these models, which make them quite complex. And one of the things that we notice is sometimes there's, the intent of the energy model is really to be a tool used by designers and engineers to help make decisions and inform direction of a design team. And I often make the comparison to structural engineering, and structural engineers use software all the time to develop structures, and they come to design team meetings and they say, okay, this is the solution. We often don't question or challenge the software or the inputs or the outputs they're using. Whereas in the energy modeling field, we often see a high level of scrutiny, some level of distrust in what's coming out of these models. And anybody familiar with having worked on projects where energy modeling was a component of it, there tends to be a lot of, as I said, distrust and perhaps uncertainty around what do the results mean? Can we trust them? Are the models sound? And the way I look at it is the math is always sound in the software. There's nothing wrong with the physics. It's how we use it. And I think what's really important to understand, the reason why I bring this up is in order to achieve better outcomes, we have to make sure we're using the tools properly, adequately, and it requires, especially in early design, the experience and judgment to be able to manipulate our tools to give us the answers we want. So it's not, we don't rely on the software. We use the software to basically do a lot of the grunt work and all the sophisticated calculations that take a significant amount of time. We leave that to computers, but we use our experience and judgment collectively as project teams, as clients and architects, designers, engineers, to take that information and make sense out of them to inform our design process. So when you boil it down, why do we ever do these models? Why do we use this software? I look at it as two main reasons. One is to optimize design towards an end goal. And I think it's really critical to have a goal. We find often that energy efficiency on its own without a specific target or numerical value, without an end goal, will always get somehow value engineer out of the project. Often, if we don't have a tangible goal, other project criteria, other project objectives will get met at the expense of energy efficiency. So it's extremely critical that on any project where energy efficiency is of concern, a goal has to be defined, and then, of course, the design has to work towards that end goal. So this could be as simple as meeting the building code in a local jurisdiction, which now we're seeing the National Energy Code for Buildings, 2011, being implemented in several provinces throughout Canada. It could be as lofty as a goal as net zero and anywhere in between. So defining a goal is critical to that process, and an energy model helps us find solutions to work towards that goal. It's often a lot easier to test things in software and a lot cheaper than to build them in a building, swap them out, try them again in different systems. So the software helps us to do a lot of that experimentation without having to build an end product. Second primary reason we use models is to manage energy-related risk. And of course that risk could be anything. Related to housing, it's the risk of cost of operation of these buildings. And if we're not managing the risk, especially, for example, in affordable housing, on what those utility bills might be, that's something we have to look at during the design stage. Some projects, for example, infrastructure projects, have financial energy-related risk. If performance objectives aren't met, then there's financial penalties associated with not meeting those performance objectives. And of course, just managing risk related to meeting whatever the target is. Like I said, if it's just code, managing the risk related to what does it take to meet code, and what happens if we don't meet it, how does that impact design and construction, timelines, budget, etc. So those are the primary reasons we would engage in the process of trying to understand energy efficiency early in design and setting up the design in order to optimize. So over the years in engaging in this energy efficiency optimization process in design, we sort of learned some things that are really critical to achieving better outcomes. The first one is it's important to be fast but not necessarily instant. Often working in project settings across any sector, we like to think of design timelines in terms of design meetings or weekly project meetings or bi-weekly project meetings. And I think if we as designers and consultants could influence design within an environment of every 2 weeks or every 1 to 2 weeks as design decisions are being made, that's extremely important. But in the energy modeling world, there seems to be this obsession with providing instant answers, where you push a button and you get a result, and that's how we're going to make our decisions. And I think that's not so much. We haven't seen that be a necessity in terms of optimizing design with energy efficiency. I think we need to be fast. You need to be current. You need to be relevant to the design. The architect and project teams and clients don't want to wait 3-4 months as the design progresses. But it's not critical that we have answers in seconds. And I think it's that balance where we need to look at. We want to provide accurate, useful information. Doesn't have to be instant, but it has to be fast and timely, and it's balancing those constraints. So the second item on here is to be accurate, not precise. I think we can all recognize that when we're trying to engage in early design decision making, we're never going to be precise to the nth decimal place. But it's important to be accurate. If we're going to inform design, we want to make sure that the direction we're setting is based on something that we can trust and rely on. And accuracy is, if we're going to provide information on energy efficiency, design options, or objectives, we have to know that information at schematic design is plus or minus 10% or plus or minus 20%. So understanding the bounds of that accuracy is extremely important. Being precise is not important. It's understanding that what we are providing has a range, has some sensitivity, and this is the range based on the information we have at this stage. Third item here is around creating flexibility, not constraints. So I'll show you an image in a couple of slides that looks at sort of how we typically look at the design process, where we say, okay, if you design the building according to these parameters, you will achieve your objective, or you won't achieve your objective. And they're very static static messages that we tend to provide in the energy efficiency consulting world. And often what that does, it says, okay, well, it tells the design team, well, okay, as long as you do A, B, C, and D, you will meet your energy efficiency criteria. But that doesn't necessarily provide the flexibility design team needs. I like to talk to architects that talk about, a list of hundreds of different objectives that design has other than energy efficiency. And for a consultant to say, well, as long as you do these things, you can meet your energy efficiency design and we'll be okay. Well, it doesn't really work within the context of them having to meet all the other project constraints that are with them. So it's important to create flexibility for the design team to help them make informed decisions and help them balance all the other requirements that they have on a project. And then, of course, communicate effectively. As an engineer, I love numbers and tables and graphs, but not everybody does. It's important that for those who are going to be making decisions related to design, how that impacts the end user, how that impacts budgets, how it impacts the architecture. All those things are extremely important to project team members. And so communicating energy efficiency in a way that provides context to all the other design team members is extremely crucial. Often we like to glaze over numbers. They don't mean much unless we can provide solutions that represent those numbers. So when to consider energy efficiency in the design? This is one of my favorite construction graphs. Let's see, so what we have here is we have a few lines. It may be a little bit confusing, but across the bottom of this graph we have the various design stages all the way from pre-design through to construction. And this first line, and maybe some of you have seen this before, the first line represents the ability to impact cost and functional capabilities. So, of course, really early in design, it's really easy to make changes. It's just a drawing. It's just a concept. It's an idea. Lots of flexibility in making design changes. And, of course, as we get to construction documents and we're on-site building, it becomes very difficult to make those changes. The second line that has an inverse relationship is line number 2 here, which shows that the cost of those changes really early in design is very low. Again, because we're not doing very much. It might just be a drawing or a concept or an idea that we're discussing, and so the cost of those changes is very low. But as we try and make changes later in the design process, way up here, the cost of those changes become quite significant. Change orders, site instructions, whatever they may be. So this this line number 3 here, which is a little bit hidden, shows that the typical design process is really the effort is heavily weighted on developing design development documents and construction documents preparing for construction. Okay, so that's our typical design process. This fourth line here shows significant effort happening a lot earlier in design, right? And that's the whole notion of the integrated design process, front-loading design, making decisions early, setting yourself up for more success and lower cost through construction. Okay, so this may sound pretty straightforward or repetitive. I wanted to put this in the context of where we often see energy modeling coming into play. And we see that, down near construction documents, it's typical for energy modeling or energy efficiency to be considered. And usually it's, here's our design, do we meet our objective? And if not, let's backtrack, let's do some redesign. What can we plug and play? What kind of equipment can we swap out in order to meet our design objective? That becomes very expensive, delays projects. So we want to try and avoid that, but it's still quite typical in project settings to do it this way. Okay, an improved method is looking at design development, and we are seeing more projects looking earlier in design development. And at that stage, most of the concepts of design are fixed, drawings are being developed, but there's still some flexibility for tweaking systems. Okay, but optimally, we really want to be involved way back here at schematic design and concept planning. Okay, and so at that time, perhaps massing is still not fixed, amount of glazing, orientation, relationship of programming, So all of these things are considered really early in design, but often not in conjunction with energy efficiency. And so really optimally, we want to be involved way back here and set the right direction forward. So why don't we see that happen more often? Okay, well, this is the what I call the energy consultant or the energy modeler or the energy efficiency expert's dilemma on your typical project. Okay, everybody wants to start the model because they want to see what the energy performance of the design is. But in order to get any meaningful understanding of how the building might behave, how this design is performing, you need inputs. You need a design. Okay, well, so we have to wait for a design, but the design's not ready yet, and the design's waiting for feedback from the consultant to inform design. And so here we are in this vicious cycle where we need information to get information. Okay, and it's definitely a struggle with a lot of disciplines, but no more so than energy efficiency, where it's really difficult to make decisions when we don't have enough information to even have a starting point. Okay, and that's why we often don't see that energy consulting or energy efficiency optimization happening very early on. So how do we break this cycle? How do we get past that? So one of the things we found is we need to use a starting point based on experience and judgment. And there's a real difference between using experience and judgment and rules of thumb. You know, one of the things that we try and get away from in terms of optimizing buildings towards really high levels of energy efficiency is to move away from rules of thumb, to use real data-driven guidance to help us make informed decisions. But at the same time, without any starting point, we will never get there. So it's really important to look at past projects, especially if we're talking about the housing sector, whether it be multi-unit residential or single family. You know, what kind of construction is it? What kind of climate? What kind of project? And using all of those project details and past experience to understand, well, based on what we've seen before, what we've done before, we can start to look at what might the impact of this design be. And of course, in order to have innovation in the design process, we don't just want to use past experience to move forward. We want to build on that past experience. We want to optimize it. We want to make it better on every single project. And so we try and embrace the uncertainty of early design through sensitivity analysis. And what I want to show you today is how we can possibly look at informing design really early on, but still having some trust in the results, even though we're making a lot of assumptions. And we're going to do that through looking at sensitivity analysis in the process. Okay, so this is what I call the status quo. If we look at a typical energy efficiency optimization process in a project design setting, we may say, okay, here is the design as presented to us, somewhere down in detailed design or construction documents. You are using, X units of energy, or you are not meeting your objective, which is that black dotted line across the screen. And then we put in a whole bunch of energy efficiency measures. Maybe it's better windows, more insulation, a different mechanical system, whatever the case may be, better lighting. And we have option one, some bundle of energy efficiency measures that brings down that energy performance. Okay, we're still not there. We're still not meeting our desired outcome. And so we might put some more energy efficiency measures, maybe even better windows, more insulation, different mechanical systems, and you present another bundle, and that's option two. Okay, great. Option two meets our desired outcome. That's the design. Let's build to that, or let's redesign to that. Okay, this is a fairly typical process, and maybe if you're really lucky, you may get 3, 4, 5, or 6 options for design on achieving that objective. But once it's set, it doesn't really leave very much room for flexibility in the design. And things always change through design development and construction drawings, and we always get questions, well, what if I had to do this? Or we found out this is too expensive. We want to cut back on the windows. It doesn't appear to be cost effective. And so now what do we do with these very static scenarios? Okay, so there's new optimization techniques out there that are accessible to everyone in every project team, and I'm going to show these with you. It's never too early to consider everything. So one of the things that's happened over the last several years is computers have gotten very good. What we can do in our smartphones, you couldn't do on giant computers 20 years ago. Or 2 years ago, for that matter. So it's never too early to consider everything. We can leverage the power of computers to do lots and lots of options and iterations and permutations of design and generate lots of data. And I say useful there because sometimes just by having data doesn't make it good. So we can generate lots of useful data. And one of the challenges that we've had is, okay, so now great, you've got thousands and thousands of data points. What do you do with it? How do you make sense of it? How do you use that information to inform design? Well, it's important to learn how to visualize that data effectively, and so one of the techniques I'll be showing, which comes from the big data industry actually, is how do you visualize all those data points and make sense of them? Using this information and these visualization techniques, we can start to learn about what the building design is. How does start to tell stories about your building? So what are the trends in the data that show where the gaps are? Where are the weak points in the design? Where are the opportunities for improving energy efficiency? Where doesn't it matter? Where shouldn't I spend my money? Okay, where do I focus my efforts? So the technique that I'm going to talk about today is called parallel coordinates, which is a multivariable graphical technique. It's dynamic, it's interactive, it's very useful in a decision-making setting to look at how various variables impact desired outcomes. It's really hard to explain without demonstrating it, and which is why I will demonstrate it. And I'm going to do it through a few case studies, and maybe not necessarily in this order. And they're all housing, of course, case studies. The first one being the high-rise Vancouver multi-residential building, which I work on a lot. And it's a very interesting building type because it has its challenges. And in Vancouver, the high-rise multi-residential building varies from market housing to apartments to social housing. You know, the concrete tower is ubiquitous regardless of what area of the housing sector you're in. And there are lots of constraints within this building sector. Constructability is a big one. When you're building high-rise towers, a lot different than single-family homes. I've heard people say, well, if two guys in a pickup truck can build an R30 wall in a house, why can't we do it in high-rise concrete construction? Well, it's a very, very different animal constructability, capital costs, consumer demand with respect to size of windows, access to outdoors through balconies. And then the outcomes we're looking for there, energy savings, whether it's energy cost, lead points, greenhouse gas emissions. So we're going to look at how all of these various outcomes may conflict with each other and how do you drive the particular outcome you want. I'm actually going to end off with this case study because it's the most complex because it's got multiple outcomes. An interesting one, which is a small multi-residential building in Inuvik, 16 one-bedroom units, about 830 meters squared. It had a design target of 50% better, so 50% less energy use than the new national energy goal for buildings, which is quite a lofty target. And so there we'll look at, you know, what is the impact of envelope, how far do you have to go in that cold climate to make that envelope as effective as it can be. We'll also look at how air leakage impacts energy efficiency. And then finally, I'll actually start with this one because it's the simplest, is a sort of single-family scenario. This is a design competition that looked at single-family cottages in a rural Ontario development, and it had a net zero requirement. So I wanted to just point out, you know, this very different objective had to meet net zero. And so what drives the envelope of this building, the building envelope ends up being the allowable PV area that's needed to achieve net zero. So a very different objective than just meeting code or, you know, percent better than a certain code. So I'm going to spend hopefully very, very few seconds here, just transitioning to the demo. Okay, so we only have this up on one screen, and it's the screen here on my right. So I'm going to, what you see might be a little bit daunting at first. I'm going to try and break it down and explain to you what you're looking at, and then go through a few examples on how this works. And again, the idea is to show how this technique of parallel coordinates, which is multivariable, it's dynamic, how it could lead to a better decision-making process on your projects. So what you're seeing here is actually about 6,000 lines on a screen, which you say, well, that's not very helpful. What does that mean? Each one of these lines here, these what I call axes, where you see heating, lighting, percent glazing, these are variables that were manipulated in a simulation tool. So this is a particular project. None of the case studies I talked about. This is just I wanted to show you the concept here, and then I'll jump into the case study. So this is a actual complex hourly simulation models on a specific project that were run. And then what we did is we used past experience to say, okay, we have the general shape, we know the occupancy, we know what this building is intended to do, and then we don't really know the design yet because we're trying to engage in an early level design decision-making process. So we just model everything under the sun that makes sense for this particular project. And in this case, it was close to 6,000 different variables or combinations and permutations of variables. And we model them, and then we bring in the results through what's called parallel coordinates, which is a visualization technique to look at all these results. So anywhere to the left of my cursor here are inputs into the model that we manipulated. So heating efficiency varying between a code compliance heating system and a higher energy efficiency one. Lighting power density, so lighting efficiency all the way down from 1 watt per square foot down to 0.6. Percent glazing, so anywhere from 40% glass to 80%. This was a high-rise tower that obviously had wanted to push the glazing ratios as high as possible. Different technologies around windows, whether they were standard code windows, improved double glazing, triple glazing, or really high performance. Solar heat gain coefficient, effective R value of the walls. And then to the right here, we have outcomes. So in this particular project, there were 3 outcomes that were important. Didn't meet code. In this case, it was a ASHRAE 90.1 code. How many LEED points under the new version of LEED could it achieve? And what is the 10-year operating energy cost of the particular design? And the reason 10 years was picked because in this case, the client thought a 10-year payback was a suitable criteria for making design decisions. So 3 separate outcomes that we're looking at simultaneously. And the line that's bolded here in blue shows one energy simulation. And so as I said, there's about 6,000 lines on here, and each line represents one simulation. So for example, this one here is, in this particular design, it has a code-compliant heating system. It's got 1 watt per square foot of lighting. It's using 40% window-to-wall ratio. It's using your standard code, double glazed window, a solar heat gain coefficient of 0.4, an effective R value of R18, and it's just meeting code for ASHRAE 90.1. It's not getting any LEED points. In fact, it's not passing for LEED certification, and its 10-year operating cost is about $4.5 million. Okay, for this, so that's what you're looking at. And what makes this tool powerful is that what happens here is that instead of trying to scramble and what we call live model situations in a design team meeting, everything is run in an office on several very large computers ahead of time. All the results are vetted and there's quality assurance on them. You trust the results, you make sure that all the inputs and outputs make sense, and then this technique allows for all the results to be seen at once and to be manipulated and make design decisions instantly. And so there's not actually any simulations happening here. They've all happened earlier. And because we have the ability to run lots of computers and computing power has significantly improved, we could run 6,000 simulations over a weekend and be prepared to answer any design question that comes and say, okay, well, what is the impact if we improve the R value from R10 to 15? Well, we have those data points. We can tell you right now exactly what that impact is. So one of the ways that this is used is, for example, I can now filter out only the design solutions that meet code. And that's cut me down from about 6,000 to 3,500. And you can say, well, not only do I want that, but I want to show me the design solutions that only get me 5 or more lead points. And now we've dropped down to only 74. Okay, and so 74 from 6,000 doesn't sound like very much, but it's still 74 different ways to achieve some desired outcome. And when you're talking to a project team that has to deal with other constraints like budget, architectural expression, programming, other design objectives, we've now allowed for some flexibility in meeting that requirement. So here at that particular desired objective or 5 or more lead points and meeting code, we see here that the only way to do that is you can have 50% or less glazing. You can't meet that high performance requirement with 80% glass. It's just not going to happen no matter what the other conditions are. Then you start seeing the trade-offs here to say, okay, well, if I want 50% glazing, I can filter the results by 50% glazing, and it shows me that I need to have triple glazing in order for that solution to work. I need to have an R value of at least 12 or higher for that solution to work. And you say, well, okay, what if I went down to 40% glazing? Well, I can now use a lower R value. I could now get away with double glazing if I had to. And so this becomes a very easy way to trade off and understand the impact of multiple design solutions. And so, of course, it can be used to do the typical design scenarios, and I'm just going to show you here. Give me a second. So I'm going to show you here, just looking at, I filtered everything out except for R value, and so for all things equal, this design now has R values varied between 10 and 20. And the energy, well, let's look at energy cost. So the energy cost you can see between R10 and R12 is about $50,000 over 10 years. And so you would weigh that against the capital cost to do that. So if my objective is to have a 10-year less payback, and the decision was to improve my R value from 10 to 12, you'd say, okay, well, is that cost effective? There's a $50,000 savings annually. Is that something that makes sense? And then as you get improved R value for this climate, which is actually a Toronto-based climate for this particular project, you can see that the cost savings start to gradually decrease. You get this diminishing returns. Okay, so we can start to investigate specific variables. We could backtrack from a design objective and manipulate the data to understand the impact of anything being considered by the design team. Okay, so I'll just show you some of the case studies that I wanted to point out that I thought were quite interesting. The first two are pretty simple. This is a net zero single-family cottage development that was being considered under a design competition. And as the goal was net zero, really the objective became, what envelope do we need so that we could fit enough PVs on the roof of these cottages in order to satisfy the net zero requirement. So I'm just going to get rid of energy because we don't really care about the energy use. We really care about if we can achieve net zero. And here, this variable that's to the far right is the square footage of PV area required. Now we know that the roof area that's available for PVs is only about 600 square feet. So I could filter out only the solutions that can meet net zero at 600 or less square feet. And here I have different levels of envelope performance ranging from very poor to around 5 up to very high at 70 for both the roofs, for all three of roof, walls, and floors, and then the window U values, the window performance as well. And you see there's lots of options on the table, but it starts to trade off. So if you didn't want to use a very good window, you start to see the lower R value performers disappearing. And if you wanted to use not very good walls, then you have to use better roofs and floors. And so you can start to filter down, and you don't make these decisions arbitrarily, you make them based on design team information. So it's actually very hard to insulate the walls because of X construction. Okay, let's fix that variable at R15 or R20 and see what it means. What do we have to have for the roof if our walls are R20 and our floor is R35? Then we need at least R35 or better in the roof, and we can achieve our net zero outcome. And so this is a fairly simple example, but in an alternate situation, what would have happened in this project is, okay, great, it's got to be net zero, it's a design competition, let's just say we're going to insulate R60 walls, R100 roof, and you get these really not necessarily buildable, not necessarily cost-effective design solutions that don't necessarily make sense or may not be required. And so this allows you to look at all the possible situations and say, okay, well, what makes the most sense within this context? What is the most appropriate solution for this outcome? And not to say that improved levels of envelope aren't important. And when you get down to whether or not you meet your design objective, you can start to say, well, okay, what if I wanted to use less PVs? PVs are expensive. Is it worth it? For every 100 square feet of PVs, I'm saving $10,000 on solar panels. What does that buy me in more insulation? Does that trade-off make sense? And you can start to make those decisions very quickly in that design setting. So kind of a unique outcome is the area of the roof is driving the performance. The next one I wanted to show is this northern housing multi-residential building, which is actually just under construction now up in Inuvik. And the same thing here, we're mainly dominated by heating measures. So we have, again, R values of walls, roofs, floors, and performance of windows. And then we also looked at LED lighting. And this became sort of one of those things where LED lighting proved to be cost effective, but it made just a drop in the bucket in terms of overall energy efficiency because it was a heating dominated building. So it was an analysis that you could have done on the side. It didn't necessarily need to be integrated with the heating measures, so we can remove that from the picture. Now, one of the interesting things about using this technique is you can start to color code by variable and look at some of the impact of, or look at some of the trends in the data. So one of the variables we looked at here was heat recovery. Now, when you're in a cold climate, one of the things that needs to get considered is that heat recovery ventilators often need frost builds up on them, and they don't operate at really cold temperatures. And so depending on the technology, some technologies can operate much colder than others, thereby recovering more heat and saving lots of energy. And we can see here that I've color-coded this outcome, which is energy use, by heat recovery technology. And the high-efficiency technology, of course, had a cost premium to it, but you can see it's blue. And so in terms of energy results, you could do everything else in terms of optimizing R values, use the best windows, roofs, walls, floors, and you still just barely going to get to any of the design solutions that have the improved heat recovery. So it becomes very, very obvious just by looking at this trend that if you don't do that, that's the lowest hanging fruit. So it's important to address that first, and you see all the blue results are in the lower, are in the bottom of the energy use curve, and so you could filter out, focus your efforts, say we're going to do that technology because it makes the most sense, and then you can start looking at how to optimize the best combination of windows, floors, roofs, and walls. Okay, so it's really useful to look at those trends or lack thereof trends in some of the data. Okay, a few minutes left here, so I'm just going to show you this one here, which is a little bit more complicated and shows how this tool becomes really effective when looking at multiple outcomes. So here we have a concrete tower in Vancouver. Again, we're looking at the typical stuff like the performance of the walls. You can see here that the R values are much different than we're looking at for our Innovic project in the range of 3.5 to 15. The reality is most high-rise concrete construction, when you take into account all the thermal bridging, its effective R values are really in the range of 5 to 10, okay, unless it's exterior insulated, which we don't see a lot of out west. And in fact, even in Ontario, a lot of towers are being built with window wall systems, so not very good performing envelopes. And we have window performance, window to wall ratio, mechanical systems, ventilation heat recovery. And then here's the interesting thing. The metrics we're looking at is energy use intensity. This is a new one, thermal energy demand intensity. If anybody's ever looked at the Passive House standard, Passive House uses a thermal energy demand. So it's basically how much heat does my building require, okay, before I add any mechanical systems to it. So it really focuses on having an efficient building envelope, an efficient heat recovery. Cost, so this is operating cost per meter squared, and then of course lead points. So one of the things to point out here is just give me a second here. So in Vancouver, it's we had a rezoning policy that was based on lead points and was driving people to a particular mechanical system that wasn't necessarily improving the envelope. And so here I've color-coded this by mechanical system, and one of the interesting things that you start to see in terms of the trends is that the colors that represent the highest lead points in blue have some of the lowest energy cost values. So to the end user, you're setting yourself up for more cost-effective operations, but they don't have the lowest energy use intensity, and they may not necessarily have the lowest thermal energy demand, so they may not be optimizing the envelope. And so in terms of which one of these are most important to you, is it end user operating cost? Is it lead points? Is it energy use intensity? Is it thermal energy demand? And so the City of Vancouver is actually struggling with, what is the right metric to drive the outcomes we want, which is low GHG emissions and long durable buildings that have really good building envelopes. And it turns out that they thought it was energy use intensity, but to get a really low energy use intensity, you could just, if I filter out, it's saying, well, as long as you use a heat pump, you're fine. You get low energy use intensity. You don't necessarily minimize costs. You don't necessarily minimize thermal demand, so you're not driving good envelopes. You can see on the far left here, I could still use a really crappy envelope and meet my really low energy use intensity just by throwing technology at it by using heat pumps. And so what they're looking at now is, well, maybe thermal energy demand is the right approach, and they're coming up with targets where, well, if we force people to drive better envelopes, use really low thermal energy demand, then the mechanical systems becomes irrelevant, and you now have to have better envelope systems. You're forced to use heat recovery on the ventilation area. You can no longer get away without it. And so this becomes a really effective tool to say, well, we had a policy, we looked at this one objective, which was energy use intensity or % better than code or lead points, and we actually weren't getting the outcomes we wanted because we didn't have all the available information. And so if the outcome we really want is low cost to the end user, especially when it comes to apartments and affordable housing, and better envelopes, then lead points or energy use intensity was not the answer. And so now if we look at this and all these objectives simultaneously, we can say, well, in order to achieve low energy cost, low energy use, low thermal demand, all those things can be weighed against each other, and then they can work backwards and devise a policy that meets all of the objectives. And so that's kind of the nice thing, is that you can put all the inputs you want to feed into the software, but also all the outputs that you're trying to optimize. Okay, so it looks like I'm just out of time. And those are the three examples. Sorry if I rushed a little bit through it. I know it's a lot to take in, but that means we now do have time for some questions, which I'm happy to answer.
Yes, excellent presentation, Christian. Daniel Pearl. One of the things that your firm is very well known for is the whole risk management, specifically where is the dew point in the wall section. As you start to look at you know, the graph easily allows you to keep on adding R value, and we very well know that at some point we can't hold all that insulation outside of the air barrier. Are there kind of notes or warnings within the software that start to say, take care, watch out, there's lots of combinations that are potentially dangerous?
Yeah, that's a great question, and it goes back to my earlier point. This is not something, we're not software developers. This is not something we sell or give access to. This is actually for us to help us do our job better in terms of communicating the best way to achieve a project's end goal. And of course, every input that goes in here represents a solution, or it should represent a solution. So what does it mean to have an R10 effective wall in a concrete tower? And what does that wall look like? And what are the implications of having that wall? And so all those things are, come along with what you see here. But this is not to be used in isolation without that knowledge and understanding of what these numbers represent in terms of actual buildable solutions. So yeah, it's a very valid point. And you can see here on the one housing project, because it was in the north and the way they were building there, we had R values up to 60, 70, which they did get. But on a concrete tower, we don't even bother because we know that that's not how they're going to build this building. So all the inputs here, yes, there's lots of simulations, but the ranges are chosen within the context of that particular project, and you have to put that in perspective.
Any other questions for Christian? Duncan?
I was wondering, can you put a number on how much this would cost in a, 10-story, 200 or less unit building? Because obviously there's some benefits here, because you can get people making the right decisions earlier, which should save them money, both in the short term and long term. So based on the cost of setting up the model and running the advice and presumably having to return to it a couple of times over the design process, can you demonstrate that the cost effectiveness is there and there's a payback to people looking to do this?
Yeah, so I think if anybody's engaging in an energy efficiency process and using modeling to do so, this would be no different. I mean, there's nothing magic about what we're seeing. In fact, we've programmed this in-house, but anybody could do it, and you could do it with any software. We decided that it was worth our investment to set ourselves up to do this very fast and effectively. So we do our models like anybody else would do on any other project using any software. And we found out that it was faster to set ourselves up to do this parametric modeling and visualization because we didn't have to return to the model every meeting and after every design meeting. It was faster to do everything up front and make decisions really early on. So in fact, it doesn't cost any more if you're already engaging in an energy efficiency, energy modeling process than you are today. At least for us, it doesn't, because we don't do projects any other way than this, because we just think you're not getting the value out of energy modeling the way it should be unless you do it in a way that's like this or similar to this process. So, I would say the fees would be exactly the same as you're used to, provided that your consultant, is incentivized to do this. And really, there are not many doing this right now, if any. But I think the industry is going this way, and this is a method that will probably become the norm over the next few years, and it'll just become the way energy efficiency is delivered. So I think on most residential projects, I like to say modeling fees and energy consulting fees range anywhere from as low as 10 to as high as 50, from your small project to your, $100 million project. It's not a large range, but that's kind of the range.
Thanks, Christian. I had a question as well. And you were certainly right. The demonstration was really important to see how this tool works with thousands of lines on there. It looks like a great spirograph or something, but when you go through it, it makes a lot of sense. And so a question I had is relating to validation of the model. And what have you done, or what do you do to try and make sure that the model results reflect what would happen in a real building?
Yeah, I mean, we get that question often is, well, what do the results mean? The building never performed as modeled. And if anybody told me a building performed as modeled, I would just fall over, because I would never expect that, right? There's a lot of assumptions that go into a model. And even if you had all the design and operational assumptions right, you're never going to get, design assumptions right in terms of R values and mechanical systems. You're never going to get the building operation right. The building hours of operation and the occupancy profiles will never be exactly as the model. You're just never going to guess it right. And so we use a lot of standards and industry norms to develop the models, because whatever you use is going to be arbitrary until the building is occupied. And we've been lucky to be involved in a lot of post-occupancy modeling, where we go back and we do what we call calibrate the models. And like I said earlier, the physics is sound, and if the models are calibrated to the appropriate weather and appropriate occupancy profiles, and the building got built the way it was designed, the models and the reality tend to match within 5 to 10%. And if they don't, what that process ends up becoming is an excellent troubleshooting process. Why is my heating 50% more? Actually, we just did a project recently, and heating valves were open in a part of the building in the summer. And so you learn things about the building that aren't optimized, not necessarily that the model was wrong. The model's idealized, and if the building isn't operating that way, there's probably something that wasn't commissioned properly or is not operating optimally. But there's nothing wrong with the physics, and as long as it's calibrated to match what's going on in the actual building, you should see results within that 5 to 10%.
Great, thanks. Any other questions for Christian? Come on.
Sure.
One of the real challenges we have is what is the role of the user in the actual operation of the building? Everything from hybrid natural ventilation to controlling how much air you have in your unit. I mean, the only slight danger of this software is forgetting about the role of the user, which sometimes some reports coming out of your own firm show the user could affect 30 to 40% of the expected results from the modeling to the actual performance. So it'd be interesting to know. I know the answer is probably just the sense of the person using the model, but I think it's interesting within a model to try and still put that in there, the importance of the user, so that the owner understands when they're going to an option that enables thermal comfort and user participation or not, I think.
Yeah, no, that's a really great point. And in some of the more complex scenarios we did this, we've put in toggles like occupancy-based ventilation, or kill switches on plug loads within a suite. And so we've toggled on and off and say, okay, or what if the thermostat set point is 2 degrees higher or lower? And so you can put in those toggles to see, yeah, if the user is operating this building differently, what is the range of performance that we should expect to see outside of that bounds? And so that's what earlier I alluded to, you know, not only looking at this in terms of design optimization, but also sensitivity analysis. So yeah, if we don't know that the user is going to use that right set point in ventilation, we could vary that and say, actually, this is your optimum answer, but if that usability varies by, you know, +2 degrees on his thermostat, we can expect to see plus or minus 5% in heating energy. And this tool is great for, again, not only design options, but also sensitivity analysis of some of those parameters. Yeah, it's a good point.
Great. So if there's no more questions, I think we're going to pause for our coffee break, a health break. The coffee's been delivered, so please join me in thanking our presenter, Christian.